Okay, we should be recording. We want to discuss infinite geometric series, right? So they bring this up really in 10F2. However, you should have been doing questions where you have an example of this already. For example, in 2B, you can see in this series, the R value is a half. These numbers keep halving. 6 is half of 12, 3 is half of 6, and so on. And when you calculated a sum with those numbers, not in that question, but in some other questions, you would have noticed that the sum didn't keep getting bigger. It converges onto some particular answer, right? The books use this word divergent here. You can think of the opposite of that as being converging. And do they use, oh, it's here, yeah, right? So for R values that are smaller than 1, or modulus R, you get this infinite geometric series. It's a bit like if you were graphing it, there'd be an asymptote and you'd get closer and closer to some particular value. Right? So let's just derive this formula here because it's quite easy to do. The formula we've already derived in class for geometric series is this one. Okay. Now what we're saying is that if R is basically a fraction, right, it can be negative, but it needs to be between -1 and 1. The book also says you could write that this way if you like, using modulus, take your R and make it positive. But I think it's easier just to see it like this. If R is exactly 1, these series don't work really. I mean, you're just multiplying by 1. So these are not smaller than or equal to signs. We're saying that R has to be a fraction, basically. It's got to be between -1 and 1. And you've seen questions like this before. The easiest fraction to think about is half, right? So, you times by, for example, my R equals a half, right? So I take my T1 and I times it by a half to the power of n minus 1, right, to get the terms. But this half here, what's happening to it? First you're going to be timesing by a half, right? Then you're going to be timesing by a quarter, then by an eighth, then by a 16th, then by etc., right? This value for what you're multiplying by for your terms is getting smaller and smaller and smaller as the powers increase. Okay? So, in the formula here, basically what's going to happen is that this is going to tend towards 0. Right? And it would just leave you with the -1. I might actually write the formula this way. Okay? So it's like I'm pulling the minus out of these. I think I did that in class for you. Imagine you came along and you divided both of these by -1, right? Then you'd have this, and you divided these two terms by -1, pull those out of the expression. You have this, and then these two minuses here will cancel and make a positive. Right? So this is the other version of the formula. Okay. But what we're saying is, as n tends towards infinity, this r to the n value effectively becomes 0. It's never actually going to reach 0, but it's going to get very, very close to 0, right? And here we don't have r to the n, right? So maybe just to explain that, I could say because r to the power of infinity is tending towards 0, right? So all you're left with then, for an infinite sum with an r that's a fraction, is a simpler version of the formula, which is nice, something that's pretty easy to calculate. Okay, so let's do there's an example in 10F1. Nice easy numbers, nice easy example that will show this to you. It's the very last question of 10F1, question 6. And I'll go back to the book and we'll have a look. It's on the previous page. So it's this one here, right? Consider this series, a half plus a quarter plus an eighth plus a... We could work out the r value. We could say a quarter divided by half equals a half. I don't think I need to do the algebra there. You can see a quarter is half of a half. Or if I was to consider term 2 and term 3, term 3, an eighth, is half of term 2. So my r value has to be a half here, right? They've also got a nice diagram showing this. We need to find S1 through to S5. So let's do that here. Right. So we've got term 1 is a half. Our r is a half. They've also written out what's going on here. A half plus a quarter plus an eighth plus a 16th. That will do dot, 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 plus on forever. And they say we want to know S1 through to S5. So what is the sum up to summing up 5 terms? Well, obviously summing up the first term just gives you a half. The next one will be a half plus a quarter, which is 3/4. The next one will be 3/4. Take your previous answer, add on your next term, eighth, so that gives you 7/8. Then you take your 7/8 and add a 16th, and you'll get 15/16. Then take your 15/16 and add on a 32nd, and we'll stop there because otherwise we'll be here forever. And we'll get 31 on 32. If I was to consider the denominators of these terms, 2, a 4, an 8, a 16, a 32, hopefully you can see that those are powers of 2. So based on that, I could say the answers to these sums are coming out as powers of 2, right? Where n is 1, I've got 2 to the power of 1, right? Where n is 1, 2 to the 1. Where n is 2, I've got 2 squared. Where n is 3, I've got 2 cubed, and so on. Right? Now, looking at the top, and what I mean by that is the numerator. The numerator, the 1, the 3, the 7, the 15, and the 31 is always 1 less than the denominator. The denominator came from 2 to the n, and I subtracted 1. Okay? So there's your formula for the sum. You can imagine then, I can see that this sum, just inspecting this equation, right? If I have an infinite sum here, I can see that it's going to tend towards 1 because as n approaches infinity, 2 to the n will become infinity, a huge number, right? And you'll be dividing by a huge number, right? These numbers are almost the same. They're only 1 different. This one's 1 smaller. So we could say it tends towards 1 from below. And we could write in a little negative to show that. All right? Gets closer and closer to 1. You could graph it as well. As starting at a half for your first term and getting closer and closer and closer to an asymptote of 1, right? Okay. Now, in this question, they want you to use the geometric series formula, which we know is T1 r to the power of n minus 1 on r minus 1. We know what our T1 is. We know what our r is. So if we use T1 as being a half, r is a half, n minus 1. And then we have to divide all of that by r minus 1. So that's a half minus 1, which will be negative a half. The negative's a bit annoying. I feel like I should have used the other version of the formula, but I've done this now, and I don't want to re-record the video. So if I'm dividing by a half, that's equivalent to what? Timesing by 2, isn't it? So we can pretty quickly deal with this denominator and say, let's times all of that by 2. Right, so I've got, well, it has to be minus 2. I've got minus 1 half to the power of n minus 1. Right, let's expand this. All right, hopefully you're following this. I'm basically just doing 2 times a half here, which gives me 1. Right. So then I end up with 1 minus a half to the power of n. This is the same as 1 to the n on 2 to the n. That was all negative. Let's move that over. Okay. We could give this a common denominator. And at this point, we've got the same formula as we had up here. I'm just wondering, are you following that? If you're watching the video, this thing here, 1 minus 1 on 2 to the n. I want a common denominator. What's the common denominator? It's 2 to the n, right? 2 to the n. Okay, how do I, my 1 has to be 2 to the n on 2 to the n. This one stays as it is, right? And I've now ended up with exactly the same formula as I had up here. To be honest, I think I liked this version of the series. It's probably the easiest one to work with. Okay. So using our geometric series formula basically gets us to exactly the same place. I'll go back to the question. It's a good question. It says, comment on S to the n as n gets very large. Well, it's going to approach 1. This saying here, explain the relationship between a given diagram. They're saying you can see that in the diagram. If you're doing a half plus a quarter plus an eighth plus a 16th, you get close to 1 as you add this all up. You can think of it as a 1 by 1 square, where we keep getting closer and closer and closer to completing the area of this square, and where the area would equal 1. Okay. What you're going to learn is that there's a simpler version of the formula, right? It only applies for these fractional r values, and it's saying instead of doing I might write it this way. Instead of doing times in the numerator t1 times 1 minus r to the n, well, this is effectively going away. It's becoming 0 because r to the n will get smaller and smaller and smaller and smaller as n approaches infinity, right? So as that n approaches infinity, we're just left with t1 on 1 minus r, right? Which in this case would equal a half divided by 1 minus a half, which is a half. How many halves? Equals 1, right? So hopefully that was clear. Now, just one final comment. The geometric series, you hopefully are noticing that I'm writing infinity a lot. So I don't want to use this simplified formula unless I know that my series is significantly long enough to use this formula, right? So if I was calculating S2, the answer is 3/4, or even S3, the answer is 7/8. I don't want to be using this formula and saying the answer is 1. By the time we get to S5 or S6, S7, maybe I can start saying, well, this sum's getting closer and closer to 1, we're converging on 1. And certainly, if we're going all the way out and thinking about this as an infinite series, if it's truly infinite, then it will add up to 1, right? Or it will converge on a specific value.